Hello wonderful person, this is Anton, and today we're going to be discussing a somewhat recent study that discusses the phenomenon confirming that the Milky Way galaxy is a bit of a monster, or a kind of a cosmic monster that for billions and billions of years seems to have grown in size by pulling in and consuming a lot of smaller neighbors and any unfortunate galaxy that came too close. And so here we're talking about various star clusters, dwarf galaxies, and even some of the larger galaxies that all eventually fell apart and became part of the Milky Way. But as we know today, these objects don't just vanish, and instead of being erased from history, they're actually stretched by tremendous gravitational forces into very long, thin formations that today are referred to as stellar streams. Formations that basically resemble rivers of stars that normally wrap around various galaxies. And though for a very long time these were very difficult to find around our own galaxy, we've seen quite a few examples from other galaxies, mostly because this is just a little bit easier to see from outside of the galaxy itself. And by discovering more of these objects, it essentially helps us establish how our galaxy evolved, helping us understand the history of the Milky Way, but also helping us understand the nature of dark matter itself. But the thing is, up until a few years ago, trying to find these and trying to detect them was actually super challenging. As a matter of fact, just a few years ago we discussed this, which was one of the biggest discoveries in terms of stellar streams. But since then, in just the last 3 years or so, our understanding and the ability to map these structures has dramatically increased, mostly because of a lot of recent and somewhat detailed surveys, such as the one created by the famous Gaia telescope, which means that now our understanding of these structures has become much better and has moved from just knowing a few of these to now having a list of over 100. So yeah, over 100 such objects have now officially been confirmed somewhere around the Milky Way galaxy. And so in this video we're going to discuss what these streams are, why they're so essential for astronomy, and of course discuss the most recent study that once again surprised everyone. But I guess let's start with a bit of a definition. So what exactly are they? And how do they actually form? Well, imagine a small collection of stars, for example inside some kind of a cluster or some kind of a dense ball of stars, or maybe some kind of a dwarf galaxy, much smaller than the Milky Way. When these objects get close enough to some kind of a large galaxy, like the Milky Way, the gravity from the galaxy starts to pull harder and harder on each of the sides of the object. This is what we refer to as the tidal effects. And as a result, it actually starts stretching the object, with the dwarf galaxy or the cluster eventually forming a kind of a line. And so here these tidal effects create two separate tails going in two separate directions, with stars moving slightly faster than the original cluster ahead of the object, which forms the leading tail, and the stars moving slower, forming the trailing tail. And because all of these stars came from the same object and share a common origin, they usually remain coherent for billions of years, and in essence form these very long stretched objects resembling a kind of a ribbon. Okay, the next question is, why are these important for astronomy? Or basically, why do astronomers care so much about them? And well, one of the main reasons is because this is basically a kind of a galactic archaeology. These are fossil records of the galactic assembly telling us how the galaxy came to be. And in a nutshell, by tracing these streams, we can then reconstruct some of the major mergers in the Milky Way galaxy, discovering how the galaxy formed, but at the same time discovering when some of the major collisions very likely happened. For example, not so long ago we discussed that approximately 4.5 billion years ago, a dwarf galaxy referred to as dwarf Sagittarius very likely passed through the center of the Milky Way, which resulted in a major formation of a lot of stars, including our Sun. And as we know today, this happened many times, basically causing periods of star formation, which formed the majority of stars in the Milky Way galaxy. And as you can expect, the passage of this galaxy basically left behind a very long stellar stream. As a matter of fact, the massive Sagittarius stream was one of the first discovered around the Milky Way, showing us a massive dwarf galaxy that's still in the process of being shredded. But at the same time, these streams can also help us track and even try to figure out the mysterious dark matter, the unusual stuff that seems to make up 80% of all matter in a galaxy, but whose origin and actual nature is still unknown. But a lot of these streams seem to be extremely sensitive to the interaction with dark matter, especially if a clump of dark matter seems to pass close to one of these streams. And that's something we discussed a few years back, when one of these streams was discovered to have an unusual gap and an unusual perturbation, which seem to be caused by something very massive and somewhat very compact passing close to it. Now, right now it's not entirely certain what this was, but researchers believe it's one of two things. Either a really massive black hole that actually should be producing a lot of other emissions, so this explanation is maybe not the best, or a massive chunk of dark matter. In other words, a lot of these streams seem to act like these giant antennae, or even motion sensors, showing us a lot of different interactions in the outer galaxy as well, allowing us to detect things we could not see otherwise. And naturally, once again, it's because there are so many of them all over the place, and even a tiny perturbation can only be caused by something very massive. But as I mentioned, for a very long time finding them was kind of challenging, mostly because they're just very faint and generally blend in with the background of a lot of other stars. And so hiding among billions of stars, we apparently had quite a few of these streams that have now been confirmed, mostly because of the famous Gaia Space Telescope. The telescope that created an extremely accurate motion of millions and millions of stars, with many of these stars apparently following the same track. And so by figuring out the precise three-dimensional positions of many different stars and even discovering their velocities, in this case it actually focused on at least 2 billion stars, it allowed astronomers to find groups of stars that seem to form additional streams, which is of course the main result from this new study you can find in the description. And so here there was a major breakthrough by astronomers from University of Michigan. 87 new stellar streams, which basically quadrupled the number of previously known streams that was only 18. And so by developing a systematic physical model to distinguish these streams from very dense formation of stars, researchers identified a variety of different objects that used to be either dwarf galaxies or various globular clusters. But one of the surprises here was that they all seem to be very diverse. And that's because previously, we always thought that all of them should be long, thin, and possibly wrap around the galaxy. But in this case, many of them were just new streams that were still being developed. And so, for example, some of them were very short and wide, indicating a slightly different mass loss history. Other ones were irregular blobs like the NGC 4147, or the strange blobs you see in this image. Here this actually resembles a kind of a circular cloud and not a river of stars. And some of them were kind of misaligned. For example, the Palomar 14 cluster don't even follow the expected orbit of their progenitor, implying that the Milky Way's gravitational field is a lot more complex than we previously assumed. But additionally, some of the streams, especially the ones from other studies, turned out to be also a little bit strange. One of them was reported in this study that was also released around the same time. And so here, a stellar stream now referred to as C19, discovered using an algorithm referred to as StreamFinder, and that actually used a lot of data from the famous Dark Energy Spectroscopic Instrument Survey, seems to be a kind of a record breaker. This is the most metal-poor stream ever discovered, containing some of the most metal-poor stars. And just as a reminder, in astronomy, this idea of metallicity or being metal-poor basically refers to having a lot of elements like hydrogen and helium and not much else. So here a lot of stars don't really contain a lot of heavy elements, implying that they seem to have formed extremely early on and are potentially some of the oldest stars in the galaxy. But despite of this, in this stream, the stars are moving a lot more hectically compared to what's expected for a stream of this mass. So in terms of motion, right now it's unclear why the stars are moving the way they are. Additionally, this also features a somewhat unusual spur of stars that's offset from the main track, which basically suggests that here there was also some kind of a violent encounter in the past, possibly once again involving a dark matter halo, or maybe a hidden massive black hole. And this is actually somewhat similar to what was previously discovered in the famous GD1 stellar stream, which was one of the most exciting stellar streams discovered in the last decade. And so here, in this case, there was a very strange prominent gap and a spur, with at least several studies proposing that a lot of these features seem to be the result of the interaction with dark matter, but in this case, a specific type of dark matter that seems to produce some kind of a self-interaction, or at least seems to form compact objects dense enough to punch a hole through this structure. And that's because right now, without this dark matter chunk, it is very difficult to explain why these gaps exist, mostly because there's really nothing else visible in this region, and like I mentioned, a black hole should be producing some other emissions, such as for example X-rays, resulting from flares around the accretion disk. And so whatever happened here, and whatever happened in this case, once again seems to confirm that the galaxy is surrounded by chunks of dark matter, which sometimes punch holes through these objects. And at least one of these chunks was also potentially discovered relatively close to us in one of the studies we've discussed in the video in the description. But because of new telescopes and because of the advances in analyzing a lot of data, we've also started to discover a lot of these streams in other galaxies, such as the recent observation from the Vera Rubin Observatory that produced this groundbreaking image featuring a spiral galaxy Messier 61. And here this stream is approximately 160,000 light-years in length, or at least 3 times longer than anything in the Milky Way galaxy. Which means that we're going to be discovering so many more of these streams in years to come, as all of this started happening just recently because of new telescopes and new ways of analyzing data. But this also of course confirms that this is a universal phenomenon and seems to happen around most galaxies out there. And so in essence, these stellar streams are actually one of the best ways for us to learn about our own galaxy, but at the same time, because of their sensitivity, seem to be some of the best ways to potentially map the invisible dark matter. And so essentially, these are some of the best laboratories we have for testing fundamental theories of gravity and modern cosmology. And so as new observatories like the Vera Rubin Observatory and the Roman Space Telescope become fully operational, instead of just finding 100 of these, we're most likely going to be finding thousands in the next few years, which will hopefully help us understand a little bit more about the universe around us and help us solve a lot of mysteries. But until these future studies, that's pretty much all I wanted to mention. We'll definitely come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying one 4% t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.